Welcome back, everyone. We're starting our second lecture over cardiovascular. Last time we wrapped up with just some of the basic discussion of blood vessels. We're going to today talk about some basic discussion of the heart. And after this lecture, we're going to start to get more into the actual functionality of the heart, and then that will lead into blood pressure. So, let's go ahead and get started with our not really attendance questions for the day. What is the function of a capillary? Which vessel would have the largest lumen, generally speaking? And blood type O positive can receive from which other blood type or types? Go ahead and pause and try to answer those. And what is the function of a capillary? Well, capillaries are where fluid exchange takes place. So this is where nutrients and oxygen are unloaded to tissues. This is where waste and carbon dioxide are picked up from tissues. Also, even though we didn't directly say it last time, when we get to the lungs, this is also where oxygen is picked up and carbon dioxide is dropped off. Which vessel would have the largest lumen, generally speaking? Veins. Remember, veins have very thin walls. They don't have a lot of pressure, so they don't need really thick walls. The walls are very thin, which leaves a lot of room for the blood. And remember, the blood is inside the lumen. Lumen, again, meaning just the generalized hollow portion of an organ. And blood type O positive can receive from which other blood types? Blood type O positive can receive from O positive because every blood type can receive from itself. And then also O negative. O negative is the universal receiver because it doesn't have, the universal donor because it doesn't have any antigens. So we wouldn't be introducing any foreign antigens. So O positive can receive from O positive and O negative. All right, well, let's start talking about some general information about the heart. And we can see kind of a picture of the heart here where it would sit within the chest. And the heart is about the size of a fist, slightly bigger, but we generally say it's fist-sized. And it weighs less than a pound. Typically, the heart weighs about 10 ounces. It sits in the mediastinum. Remember, the mediastinum was that one cavity that didn't really get a lot of attention in Bio 137. If we looked inside the thoracic cavity, the chest cavity, it had a left and a right pleural cavity where each lung was found. And then in between those pleural cavities was the mediastinum, which filled up the middle portion of the chest and the lower part of the neck. And inside the mediastinum was where we found the pericardial cavity, and that's where we find the heart. And the heart is smack in the middle of the chest, right behind the sternum, that hard bone in the middle of your chest. But about 2/3 of the mass of the heart is on the left side. So we'll talk a little bit about that more here in just a little bit. But because of that mass difference on the right and on the left, the heart kind of curves a little bit. You can see it here a little bit in the picture, and it comes to a point right here. And this point is called the apex. And the apex points roughly towards the left hip. Now, there's a lot of stuff on your outline about filling out the anatomy of the heart, and most of that is self-study, and you can fill that out, let me see, on page 711 and 712 of your textbook. That's where the anatomy portion of the heart is covered, so I'm not going to go into that a lot, but you do want to go ahead and fill that out because that's also part of lab, and I am not making a lab video of the heart anatomy for the heart model. I am going to make one for the actual heart, but the heart model I'm not going to make a video for. So you can fill most of that out. I will talk about just some very general stuff here while I've got this image up. And that's first on this top part of the heart. So the superior part of the heart, there's two chambers. There's the right atrium and the left atrium. And if we're talking about both of them, we say atria. One is an atrium, both together are atria. And the atria are receiving chambers. Blood is coming back to the heart and it enters either the right atrium or the left atrium. From the atrium, it moves through a valve into the ventricle, and then at the bottom of the heart, or the inferior portion of the heart, the ventricles are ejecting chambers. So when the heart contracts, the ventricles push blood out of the heart, either to go to the lungs or to the body. And then the large blood vessels on the top part of the heart are called the great vessels. The great vessels are the large vessels that either enter the atria or leave the ventricles. So real quick, on the right side of the heart, we have the superior vena cava and the inferior vena cava, which return blood to the right atrium from the rest of the body. Then blood flows into the right ventricle, and when the right ventricle contracts, it pushes blood up into this vessel called the pulmonary trunk. The pulmonary trunk immediately splits into left and right pulmonary arteries, and those arteries take blood to the lungs. Over on the left side of the heart, here we have the left atrium, and the left atrium has these thing called the pulmonary veins. There's two coming here from the left lung and two over here coming from the right lung that empty into the left atrium. Blood moves down into the left ventricle, and you can't see it right here, but this big vessel right here is called the aorta, and it kind of passes behind all of this right here and connects to the left ventricle. So when the left ventricle contracts, blood is pushed out into this aorta, which carries blood off to the body. Now there's a little bit more as far as, vessels and the papillary muscle and the Purkinje fibers and the valves here. So there's more to the heart, but like I said, all of that is in your book on page 711 and 712, so you can easily fill that out. If there's any of it that you want help with, just let me know. I do want to talk about some disorders, and one of these disorders up here at the top does talk about a structure in the heart right here called the Fossa Ovalis. Now, when you are an adult, well, really even a child, after you are born, blood comes into the right atrium from the body, it goes into the right ventricle, and then up into the pulmonary trunk, and eventually off to the lungs to get oxygen. It comes back from the lungs fully oxygenated into the left atrium, down into the left ventricle, up into the aorta to go supply the body with that oxygen. But when a baby is still in mother's womb, it's not breathing, so it really doesn't need to send blood to the lungs. It's actually getting all of its oxygen from mom by way of the placenta. So it's kind of a waste to have blood go to the body, come back, and then go to the lungs, and come back, and go to the body, and come back. Instead, it would make a lot more sense to just keep sending blood to the body, to the body, to the body, to the body. There's no real reason to send blood to the lungs. So instead of this little structure right here called the fossa ovalis, there's actually a hole in the wall of the right atrium when the baby is still in the womb. And that hole is called the foramen ovalis. So what actually happens when the baby is still in the womb, as blood comes back to the body into the right atrium, a lot of that blood goes through this foramen ovalis, which passes into the aorta so that it can then go off to the body again. There's still going to be some blood going down into the right ventricle and going to the lungs, but it's not really serving much of a purpose. So a lot of the blood takes a shortcut from the right atrium through the foramen ovalis into the aorta and off to the body. Now, when the baby is born, there's a reflex that happens. When baby takes its first breath, that triggers a reflex which causes this foramen ovalis to seal into the fossa ovalis. The fossa ovalis is basically a scar that's left over where that foramen used to be. So when a baby is born, doctor listens for the cry, because if the baby is crying, it's breathing. If the doctor doesn't hear the baby crying, he gives him a good whack. Not enough to hurt the baby, but enough to scare it a little bit. And the baby starts crying, and that means that the baby is breathing, and that sets off the reaction, resulting in the closure of the foramen ovalis into this fossa ovalis. Now, sometimes the foramen ovalis does not completely close, and it's common you'll hear someone say the baby has a hole in their heart. Now, there's different places where this hole can occur, but the vast majority of the time, what they're talking about is this area right here that did not fully close. And it's actually really common. Doctors can go in and close that if it's a large enough hole that it makes much of a difference. Next thing we want to talk about are murmurs. Now, there are normal heart sounds that we'll talk about in just a little bit that come from closure of these valves. There are 4 valves in the heart. There are 2 valves in between the right atrium and the right ventricle, the left atrium and the left ventricle. So these are called AV valves, or atrioventricular valves. There's better names for them, so I'm going to go ahead and tell you what those are. On the right side, the right AV valve has 3 flaps, so we call it the tricuspid valve, and that's what I'm going to use in this class. The tricuspid valve is in between the right atrium and the right ventricle. Its job is to allow blood to flow from the atrium into the ventricle, but prevent blood from going back the other way. Over on the left side of the heart, there's the left AV valve, which has 2 flaps. We call this the bicuspid valve. So that's what term we're going to use in class, is the bicuspid valve. The bicuspid valve lets blood flow from the left atrium into the left ventricle, but not back the other way. The other 2 valves are called semilunar valves. The semilunar valves are in between the ventricles and whichever great vessel leaves that ventricle. So here we can see the valve that's in between the right ventricle and the pulmonary trunk. This is called the pulmonary semilunar valve. Here we can just see a little bit of this guy right here that's in between the atrium and the base of the aorta. This is called the aortic semilunar valve. So we have 4 valves, and when they close, they make a sound. Now those are when someone's listening to your heart with a stethoscope. That's what they're listening to. They're listening to the closure of those valves. If you've ever used a stethoscope, I know most of you probably already have your CNA, so when you're listening to someone's heart, you're hearing those valves close. Okay, so those are called the normal heart sounds. But there's something called a murmur, and there's a lot of different types of murmurs. So murmurs is a class of disorder, and they are abnormal heart sounds. When those valves don't close correctly, it makes a weird sound called a murmur. Now, like I said, there's a lot of different types of murmurs, but we can often group them into two big categories. There are other types, but these are the two big common ones. First, we have incompetent valves. And incompetent valves, when they close, they don't close all the way. We said that these allow blood to flow one way but prevent it from going the other direction. Well, if they don't close all the way, then what happens is blood can flow back the other way. And this makes an extra kind of swishing sound. When the valve closes, there should not be any sound in that area. But if the valve doesn't close all the way, there is a little bit of sound as blood goes back the other direction, and it sounds kind of like a swoosh. The other type of murmur is called a stenotic valve or a stenosed valve. And here, what happens is the valve doesn't open wide enough, typically because the valve has hardened. Maybe it's calcified, maybe it's got buildup of some sort. But whatever it is, the valve does not open all the way. The opening is narrow. So as that blood goes through, it kind of makes a high-pitched wheezing noise. It almost sounds like a whistle or something similar. And these are bad because it causes the heart to have to work harder to move the same amount of blood. Now let's use a thinking cap question. Why do you feel the heartbeat on the left side of your chest? Well, let's go back to look at that picture here. The heart's not on the left side of your chest. It's in the middle. But the left side of your heart is much thicker. If we look at the wall of the left ventricle versus the wall of the right ventricle, the wall of the left ventricle is significantly larger. Now, we're not in lab, so I can't really show you on the real heart until you watch the lab video, but that wall of the left ventricle is thicker than the width of your thumb. The wall of the right ventricle is thinner than the width of your pinky. There is a real big difference in the size of those walls. So if we go back and we look, you can't really tell here. You can tell a little bit, see how thin the right wall is versus the left wall, but even this doesn't do it justice. But the reason is the right ventricle, when it contracts, it's pushing blood to the lungs. Where are the lungs in this picture? They're right next to the heart. So it's not a really long path. But the left ventricle, where is it pushing blood to? It has to supply blood to the entire body. So it has a lot more work than the right side does. So the right ventricle doesn't have to be very thick. The left ventricle does need a lot more thickness because it's a lot more muscle, a lot more power behind the contraction. So when we feel the heartbeat, really what we're feeling is this area right here. This is called the apical pulse. And all in this region right here, we feel the heartbeat because the left side of the heart has to work a lot harder to push blood to the entire body. So next time you're, at a sporting event or whatever, and they tell you to stand for the national anthem, or you see someone doing the pledge or whatever, and they're putting their hand over their heart and their hand is over here, you can point at them and mock them, and don't really do that because they're probably going to take it out on you. But, in your head, you can think they don't know where their heart is. So let's talk about blood flow. Now, when we're looking at the heart, the right side of the heart, which it's kind of difficult to tell, but really the right atrium is right here. The right ventricle is all of this area right here. The left atrium is kind of hidden. We can see a little bit of it right there, but it wraps around. That's the left atrium. The left ventricle is right here, but most of it is on the back of the heart in this view, so we don't really see it. But as kind of a cheat, a giveaway, this set of blood vessels right here are what divide the outside of the heart. Everything kind of above and to the left in this picture, but really it's above and to the right. This is the right side of the heart. Everything kind of to the right and below, to the right in this picture, really to the left and below the heart, or this set of vessels here, is the left side of the heart. So the right side of the heart contains deoxygenated blood, because blood is coming back from the body into the right atrium. It's already dropped its oxygen off. And then once it gets to the right ventricle, and now it's going to go off towards the lungs, but it hasn't gotten there yet, so it's not carrying a lot of oxygen. The right side of the heart contains deoxygenated blood. The left side of the heart contains oxygenated blood, blood that's coming back from the lungs, carrying a big supply of oxygen, and then getting ready to get sent off to the body to drop that oxygen off. And when we look at the heart, there's really what we call two circuits. There's the circuit that goes from the right side of the heart to the lungs, and then back to the left side of the heart. This is called the pulmonary circuit. The pulmonary circuit flows from the right ventricle to the lungs and back to the left side of the heart, into the left atrium. Its function is to go to the lungs to drop off carbon dioxide and to pick up oxygen. The pressure is pretty low. It doesn't have to be very high at all because, like I said, the lungs are right next door. And then the other part is called the systemic circuit. The systemic circuit is blood flowing from the left ventricle to the body tissues and back to the right atrium. And its function is to deliver oxygen and nutrients to the body and to pick up carbon dioxide and waste and bring back to the heart. The pressure here is much higher because the blood is being pushed by the left side of the heart off to the body. But now really there's also something else called the coronary circuit. I don't believe I have a slide of that. I do. The coronary circuit really is a part of the systemic circuit. So let's go back to the picture. We can see the heart has a lot of blood vessels. Well, now the heart is full of blood, but the blood that's inside the heart is not of any use to the heart itself. It's just flowing through. But the heart muscle is constantly working, so it needs a lot of oxygen, a lot of nutrients, so it has to supply itself with oxygen and nutrients. And that's what all these blood vessels on the surface of the heart are. And it's, like I said, it's a part of the systemic circuit. The heart is considered part of the body, not part of the lung. So there's blood flowing all across the surface of the heart in those blood vessels. And as those blood vessels return blood to the heart, that blood is going to be emptied into the right atrium. And it's being returned from quite a large vein called the coronary sinus. The coronary sinus is a vein that runs on the surface of the heart and returns blood to the right atrium. So really the right atrium is receiving blood from the upper part of the body in the superior vena cava, the lower part of the body in the inferior vena cava, and the heart from the coronary sinus. Now, sometimes some of these heart blood vessels will get blocked. And if they start to get blocked, then when the heart is beating, when it's being worked and it's starting to need more oxygen, if it's got a little bit of a blockage, not enough oxygen is going to be supplied. And think back to Bio 137. When cells, especially muscle cells, are using oxygen faster than they are being supplied with oxygen, what happens? something called lactic acid builds up. And lactic acid, which is an acid, it starts to hurt. It starts to burn as it builds up in those muscle cells. And that burning sensation kind of feels like a crushing pain in your chest. And that's called angina pectoris. That literally just means pain in the chest. Angina pectoris is what happens when there is a slight blockage in some of the small vessels of the heart that are supplying the heart muscle. So as a result of that, we start to get a buildup of lactic acid, and we get pain. The pain is the result of that lactic acid building up due to low oxygen. Now, if you sit down and you take a rest, then that pain will start to go away because you're not demanding as much of the heart, so it doesn't need as much oxygen. And when you rest and the pain goes away, you think, oh gosh, I thought I was having a heart attack, but I guess not, because rest made the pain go away. But what if that blockage was more severe? What if we completely blocked a vessel on the surface of the heart? Well, now, as that oxygen starts to be used up, we can't supply any more oxygen to that specific part of the heart because the vessel supplying that specific part of the heart is completely blocked. So again, you start to get that pain from lactic acid building up. And you sit down to take a rest, and the pain doesn't go away. That will then lead to a part of your heart dying because there's not enough oxygen there. And when some part of your body doesn't get enough oxygen, it will die off. When a part of the heart is deprived of oxygen and it starts to die, that's what we call a myocardial infarction, which is a heart attack. A heart attack is the result of complete blockage of at least one vessel in the heart. And when that happens and lactic acid builds up and there's no oxygen, that part of the heart will die. Myocardial infarction, heart attack. So the last thing that I want to talk about in this lecture is going to be the path of blood through the heart. Now, I will tell you, when I hold my class in person, this is the other question that I always tell them is going to be on every single exam. It's the path of blood. Now, in an online class, I'm still going to have some variation of path of blood, but it's not going to be as in-depth as what we look at here, although I still want you to learn this entire path. If you learn this path and you know it like the back of your hand, when you get to your program, you are going to be miles ahead of every other student there. So let's go ahead and draw the path of blood. Now we can draw the path of blood beginning and ending anywhere. It doesn't really matter because it's a complete circuit. But I always start, and books always start, in the same spot, and that's going to be the right atrium. Now, I'm going to use a lot of abbreviations, and anytime in my class, if you want to use an abbreviation, you are welcome to use it as long as it is an abbreviation you have seen me use in class. So we're going to start in the right atrium. Now, a couple things that I want you to notice. RA, right atrium, it's in blue ink. I'm using blue ink, and this is going to represent all of the areas where blood is low in oxygen. And I'm also going to put a square around this because I'm going to put a square around all of the chambers of the heart. So we're starting in the right atrium, and now we're going to trace the path of a drop of blood through the entire circuit. When the right atrium fills up with blood, that blood is going to move into the right ventricle. But before it does that, it's going to pass through the tricuspid valve. Now, valves, I'm going to put a circle around. So squares are going to go around the chambers. Circles are going to go around the valves. Blue is going to represent blood that is low in oxygen. So from the right atrium through the tricuspid valve, we go into the right ventricle. When the right ventricle contracts, it's going to eject blood. Blood is going to be pushed out of the right ventricle through the pulmonary semilunar valve into the pulmonary trunk. The pulmonary trunk. So now we've left the heart. We're on our way to the lungs. The pulmonary trunk almost immediately splits into right and left pulmonary arteries. The right pulmonary artery is going to take blood to the right lungs. The left pulmonary artery is going to take blood to the left lung. So that's what right and left here means. Now, we're going to get smaller and smaller and smaller. We're going to go into arterioles. From the arterioles, they're going to get smaller and smaller and smaller until we're in the pulmonary capillaries. Of the left and right lung. Now you can see here that the pulmonary capillaries of the left and right lungs, I've written half of it in blue, half of it in red. And that's because when blood shows up, it's low in oxygen, but while it's there, it picks up oxygen. So now I'm going to use red ink for all of the spots where blood is high in oxygen. As we leave the pulmonary capillaries, we're in the venules. Now we're in the left and right pulmonary veins. The left pulmonary vein brings blood back from the left lung. The right pulmonary vein brings blood back from the, The left pulmonary vein brings blood back from the left lung. The right pulmonary vein brings blood back from the right lung. That's a tongue twister. Both the left and right pulmonary veins are going to dump blood into the left atrium. Now we're back at the heart. The left atrium passes blood through the bicuspid valve into the left ventricle. When the left ventricle contracts, it's going to push blood into the aorta, but blood has to pass through the aortic semilunar valve. And then blood exits the heart into the aorta. The aorta is going to send blood off to the body tissues. So we're going to get smaller and smaller and smaller arteries. Arterioles. The capillaries of body tissues. And again, we see that I've used two different colors of ink because as blood arrives at these capillaries in the body tissues, it's full of oxygen. But while it's there, it drops that oxygen off. Remember our capillary fluid exchange. So when blood leaves those capillaries in the venules, it's low in oxygen. It starts to go through veins until we get to the superior or inferior vena cava. Superior drains the upper part of the body. Inferior drains the lower part of the body. And each of them return blood to the right atrium. So on an exam, what I would usually do in an in-person class is I would say, trace the path of a drop of blood from, and I would pick a spot, let's say the pulmonary trunk, to the capillaries of the body tissues. So what you would do is start at the pulmonary trunk and list all of the spaces that you pass through until you get to the capillaries of the body tissues. And then I would say underline all areas where blood is high in oxygen and put a star next to any areas where it changes from high to low or low to high. So you would underline all of this red and put a star next to the pulmonary capillaries and the body tissues. So like I said, I'm not going to ask you to write this out on any of the exams. I will ask you questions, so you still want to know this. But even if I wasn't going to ask questions, I would still really suggest writing this out on a piece of paper, writing it again until you could reproduce this at the drop of a hat. Because when you get to your programs, if you know this, you are so far ahead of everyone else. All right, so just to kind of wrap it up, even though we talked about the pulmonary circuit and the systemic circuit, I would like you to keep in mind that is a very oversimplification of how it goes. There is the pulmonary circuit. But when we talk about the systemic circuit, there are many paths that it could take. It could go to the upper part of the body, like the head and the upper limbs. It could go to the liver. It could go to the stomach, the intestines, and back to the liver. It could go to the kidneys. It could go to the lower body, the lower abdomen, the legs, whatever, and back to the heart. So when we talk about the systemic circuit, there really is a lot more to it than the way I presented it. But you do not need to know all of this detail. This is just to give you an idea of, hey, there really is a lot more to the story. Okay, so that is where we're going to wrap up today. Next class, we are going to talk about the cardiomyocyte anatomy. We're going to look at the structure of the muscle cells in the heart. And then we're going to start talking about something everybody loved in Bio 137, and that is action potentials. And we're going to see really at the microscopic level, how does the heart actually contract? All right. So if you're not really comfortable with action potentials and muscle contraction, go back to some of the Bio 137 material that you have or in the textbook and refresh yourself just a little bit, because we're going to hit the ground running next class, and I will talk to you then.